Dear students, I welcome you all to the next session of digital communication. So, in this class, I will explain what is modulation, the classification of modulation, the different types of analog and pulse modulation schemes, and thereafter, we will discuss in detail the pulse modulation and demodulation. So, I think the word modulation is quite familiar to you. So, you have already completed analog communication course in the previous semester. So I hope you know the fundamentals of modulation. You know that the definition of modulation is the process of changing the characteristics of a high frequency carrier according to the instantaneous amplitude of message signal. So in this context, we have two parameters, the modulating signal. What is a modulating signal? Of course, this is the actual message to be transmitted. Now, then what is the function of this carrier signal? Of course, this carrier is a high frequency signal and this is the actual signal being transmitted. So whatever be the application, whether it be a TV or radio, we are not transmitting the modulating signal as such, but we are transmitting the carrier signal after modulation. Now, always the carrier will be a high frequency signal and the modulating signal will be a low frequency signal. The carrier after modulation is called as modulated signal. Okay, so what is the need for modulating a signal? Of course, you know that the length of the antenna required should be at least 1/4 or λ/4 the transmitted signal wavelength. So higher the frequency, lower will be the wavelength. So for any practical requirement, the antenna length will be reduced. But if you are transmitting the message signal, the low frequency message signal as such, it would require antennas with large dimensions. Okay, so the height of the antenna required will be very large. But after changing the characteristics of a high frequency carrier signal with respect to the information signal or the message signal and transmitting that modulated signal, the antenna requirement, the length of the antenna required will be less. And in practical aspect, we know that if we listen to radio, an FM radio, we have a lot of channels like 91.9, 94.3, 93.5, etc. So all these channels are specified with the help of some frequency, is it not? So 91.9 is nothing but the carrier frequency of Radio Mango. Okay, likewise, each transmitting station is allocated with a particular carrier frequency. Okay, so the channel can be selected by properly tuning to that particular carrier frequency. For television application as well, for all these stations or all these channels, a particular carrier frequency is allocated and the channel will be transmitting on that particular carrier frequency. So it is actually the carrier which is carrying the message from the transmitter end to the receiver end. I hope you understood. The modulated signal is the carrier after modulation. Now we will see the classification of different modulation techniques. Modulation schemes can be broadly classified under two headings: continuous wave modulation and pulse digital modulation. Continuous wave modulation is also called as analog modulation, and we can see from this diagram the continuous wave modulation is again divided into amplitude modulation and angular modulation. This amplitude modulation is our familiar AM, and under angular modulation or angle modulation we have frequency modulation or FM and phase modulation or PM. Now, the next classification is digital modulation or pulse digital modulation. And under this, there are two subcategories: digital pulse modulation and analog pulse modulation. Okay. In digital pulse modulation, we have pulse chord modulation. There are a lot of other examples as well. Okay. DPCM or differential PCM and delta modulation. And under analog pulse modulation, we have pulse amplitude modulation, pulse duration modulation, and pulse position modulation. So this is an important question for your examination point as well. They will ask you to list the different types of pulse modulation techniques. Okay. So in these areas, in pulse digital modulation schemes, we will concentrate more. So to start with, we will discuss what is PAM or pulse amplitude modulation. Okay. So we'll discuss the first method of analog pulse modulation called as pulse amplitude modulation or PAM. PAM is an analog modulating scheme in which the amplitude of a pulse carrier varies in proportion to the instantaneous amplitude of the message. Okay, so here in analog pulse modulation, the message is analog and the carrier is a pulse-like waveform. Okay, so according to the instantaneous amplitude of the message, the pulse amplitude of the carrier is varied. So if you represent PAM using a waveform, so this is the modulating signal or the message signal. Now we have the carrier pulse train, it is a pulse waveform. Now in natural PAM, the amplitude of these pulses are getting varied. Okay, according to the instantaneous amplitude of message or modulating signal. So here we can say that when the amplitude is positive or increasing, the pulse amplitude is increasing. Okay, and when the modulating signal amplitude is decreasing, the carrier pulse amplitude is decreasing. Okay, so the shape of this envelope, the shape of this PAM waveform will be exactly same as that of modulating signal. You can see here, this is the envelope and this PAM envelope is also exactly the same. So we can compare this with our analog modulation scheme, the amplitude modulation. In AM also, the amplitude variations of the AM signal is very similar to that of the modulating signal. Okay. Now, we will discuss how such a waveform is generated or what are the methods of generating a PAM waveform. So this is very important for you as far as the exam point is concerned. We have a circuit arrangement for obtaining the PAM waveform. We can see here, this is a circuit having two switches. Okay, these two field effect transistors are acting as switches, basically an electronic switch. The first transistor is represented as a sampling switch. The second one is represented as a discharge switch. And there is a capacitor. Okay. So in practice, what is done is, we apply the message or the modulating signal across the input point, and then the carrier's pulse or the pulse train which is acting as the carrier is applied to G1, and the same pulse signal after inverting. So after inverting, the same carrier signal is applied to the gate of G2. Okay. So we have a pulse train here which is directly applied to the sampling switch, and the same pulse train is applied to an inverting amplifier, and after that the inverted form of this pulse is applied to G2. Okay. So when G1 is on, when the first transistor is on, the second field effect transistor will be off, and when the first is off, the second will be on. So this will be the case. Okay. So what happens? Let us see what happens when we are applying this modulating signal. So just look at the diagram. You please follow the cursor movements. Okay. So this is the modulating signal that we are applying. So at this instant, when this is the amplitude, okay, suppose the carrier pulse is, so this is the carrier pulse train. So this is on, then off, on and off. Okay, is it not? The carrier pulse train is a waveform having on and off transitions. So when the carrier pulse is on, okay, when the carrier pulse is on, this transistor gate, we are applying the pulse train to the gate. So the first transistor will be turned on, whereas the second transistor will be turned off. I hope that is clear. Listen. So when we are applying the first pulse, the first transistor will be on, whereas the second will be off. So of course, the capacitor will charge through this path. Okay. So this is the charging path of the capacitor. It won't charge through this path because this switch is acting like an open switch. This is off. Okay. The capacitor will charge to the then maximum value, whatever be the maximum amplitude at that instant. So the capacitor is charging up to that maximum value. After that, for the next time slot, when the pulse amplitude is 0, what happens? Okay, you know that the first transistor will be turned off and the second transistor will be turned on. Okay, so in that case, the capacitor will discharge through G2. So when the pulse train is on, G1 is turned on, capacitor will charge, and when the pulse train is off, G2 is turned on and capacitor will discharge to 0. And again, when the next pulse arrives, the same process is getting repeated. G1 will again charge to that maximum amplitude. So initially capacitor charges to this maximum amplitude, thereafter it discharges. Okay, and then the capacitor charges to that maximum value. Alright, and thereafter the capacitor discharges. Okay, so the process is getting repeated for the entire cycle of this carrier pulse. Now in this circuit, since we are using a capacitor here, we are getting a PAM with constant amplitude. Constant amplitude of flat top. Okay, these amplitude values are flat. So in the previous diagram, this PAM, this is natural PAM where the amplitude is varying. But in this case, the amplitude is remaining a constant. Okay. So this is the working principle of this particular circuit. Charging and discharging of that particular capacitor. Now going to PAM demodulation. The PAM demodulation process consists of, so this is the block diagram of PAM demodulation. So we have a holding circuit and a low pass filter or LPF. So at this point we apply the PAM signal. It is applied to a holding circuit. So this holding circuit is converting the signal into a waveform like a stair step. And after that, this is low pass filter to obtain the perfect original information or the demodulated signal. We'll explain the circuit. So in this circuit, we use a switch and a capacitor. So this is our PAM waveform. So you can see here, look at the diagram, just follow the cursor movements. So listen here, see, these are the amplitude variations. See, these are the amplitude variations of the pulses. So this switch S will be closed when the pulse is on. I repeat, this switch S will be closed when this pulse is on, and the switch is open. The switch will be open when this is 0 or when the pulse amplitude is 0. So this is our PAM waveform. We are applying this PAM waveform across the two input terminals. Okay. So when during T on, when it is on or high value, the switch S will be closed. So what happens to the capacitor? Yes, of course, the capacitor will charge. Okay. And when the switches for the next time slot, this waveform is 0. At that time, the switch will be open. Since there is no path for the capacitor to discharge, the capacitor will hold the value, okay, or it will retain the value up to which it has charged. Okay, so it will retain the sample value, or it will retain this charged value. Okay, so when the pulse is on or when the pulse amplitude is high, the switch is closed, the capacitor will charge, and when the pulse amplitude is 0, this capacitor will not discharge, but it will hold that charged value. Okay, so in between the pulses, so this is the first pulse and this is the second pulse. In between the pulses, the capacitor will be holding the previous sampled or previous charged value. Okay, so the cycle is repeating. Now if the next pulse is arriving, if this pulse is arriving, again the switch S will be closed. Now the capacitor again will charge up to that maximum point, and when during this time slot, switch S will be open. So since there is no path for the capacitor to discharge, it will hold the maximum value. Okay, so at the output of this holding circuit, we are obtaining a waveform like this. Okay, so this is the holding circuit. So after applying this PAM signal into a holding circuit, we are obtaining a waveform like this. So we can see here, this is just like, it resembles our original message signal, is it not? So if you are applying this waveform to a low pass filter circuit, we will obtain the perfect or the original message signal as it transmitted. Okay, so here we can see this is the holding circuit. At the input we apply the PAM signal. At the output we are obtaining a stair-step waveform like this, and after removing the high frequency ripples from this waveform using the slow pass filter, we obtain the original message. So this stair-step variation will be the output of holding circuit. So we are applying this signal into a low pass filter to obtain our original message. So this is about the working principle of the demodulator. So I have already explained. And the exercise question for the 4th session. Draw the circuit of an LPF, a low pass filter using resistor and capacitor. Draw the circuit of a low pass filter using resistor and capacitor. So please send answer for this question so that I can ensure that you watch the video. Thank you.